Well, what a chapter. Chapter 8, trig. Pretty basic, but there's a lot of abstraction to it. So just keep practicing. And in fact, today's a pretty short lesson. So I threw in another review question. Yes, hopefully at this stage you're kind of going, wait a minute, I'm feeling the rhythm. So let's just walk ourselves through it. We want to find all angles. So a couple things I noticed about that is it's in degrees and it's not your basic 0 to 360. So we're going to find our two critical angles and we're going to add and subtract to make sure we get all the possible angles in that range. So randomly, we picked 7, 8, 9. All right, that's too bad. That's why 9 was afraid. Oh, 6 was afraid of 7 because 7, 8, 9. Okay. All right, sine, we find the first angle, use our calculator. Sure, if 0.789 was something like square root of 3 over 2, maybe we rely on our unit circle knowledge, but the calculator always works. We get our first angle, we loving that. All right, so at this stage, hopefully you know there's 1,001 identities, but there's three that really help us find the angles. One's sine, one's cosine, and one's tangent. Maybe you've simplified them to these rules. If not, this would be a great thing to have in your notes. Since it's sine, we find the second angle by subtracting it from 180. We're in degrees, so we're going to use that bad boy right there. All right, so we subtract from 180, we get our second critical angle, 127.9. We have our two critical angles. Now it's all about figuring out which ones fit in that negative 90 to 450 degree range. Now this is way overblown. I'm really just trying to make sure that you understand what I'm doing. I'm starting with my critical angles here and I'm adding and subtracting 360 to kind of show you all the possibilities. And then it's up to me to go back and grab the ones that I want. Now, in reality, I know when I subtract 360 right here, I know I'm going to get further than negative 90. So I probably wouldn't even write this, but I'm just trying to be very clear about what I'm creating so that I can go grab all the solutions. Some of it is intuitive, like, oh, I can see that I don't need to subtract 360. And some of it, you just need to do it and see it and then cross them out. So once I've taken this, I find that the solution, the two initial ones both fit. They may or may not fit in the range. You know, we know that they work. That's great, but I got to make sure they still fit in the range. And it turns out there's one more that fits. Everything else is outside of that negative 90 to 450. Cool. Hopefully that's like, oh, come on, Serge. I want you to be comfortable and confident because once we get into other chapters, when we get down to this, I want you to go, oh, I got that from there. All right, today we are doing non-right angled triangle trigonometry. And in other words, not the world doesn't live with right angles all the time. Now, I'm going to make this very clear. The stuff that we see in this chapter works for all triangles, okay? Meaning some people are like, well, I've got this cool little rule, but that's a right triangle, so I don't think I can use it. Yeah, there might be a simpler rule for a right triangle, but please understand these processes work for all triangles. Hey, today could be easy. The area of a triangle, that's it. Well, we already know the area of a triangle is our good friend uh, 1/2 base times height. So when you have a right triangle, that's pretty sweet. The base and the height are already at 90 degrees. We're good to go. When you do not have a right triangle, then whatever side you choose to be the base. Oh, Mr. Sayers, it's got to be the bottom. No, it doesn't. It doesn't have to be the bottom. Whatever side, then you need to draw this horizontal or this vertical line, vertical. How about this perpendicular line to the base, to the opposite vertex? Okay, so that's kind of how we see it. We see this pretty easily in this triangle. Here we have the line containing the base and we draw the line perpendicular to the base to that, and that's going to represent our height. Awesome. So where do we run into a little bit of trouble? Uh, it's like, well, we're given this information. How do we go get the height in an acute triangle and an obtuse triangle? Well, it turns out there's one way, always works, given a side angle side situation. And that's really, I'm going to plant that seed right now. What we're going to be dealing with, or hopefully you recognize when I have two sides in the included angle, I'm going to go ahead and use this formula. All right. Hey, little FYI, just when you label a triangle, the angle measures are all capital letters, and the side lengths are going to be the lowercase of the opposite vertex. So if this is B, this other side is lowercase b. Great. Why, Sarah? Why are you doing this? Because sometimes problems are just written and there's no picture, and they say capital A is 38 degrees and lowercase a is 17 centimeters. It's good to know that they have a relationship. They're opposite in the triangle. All right, so here we are in our situation. We have labeled this triangle ABC. We labeled it the sides. So we always start out with the basics, 1/2 base times height. We'll take this to be our base. Cool. So that is easily, we put that in there. And then the height, good old h, darn it. I wish I had h in terms of B and C, okay, B and C. So if you put yourself right here, you can see that you are part of a right triangle. And hey, we have SOHCAHTOA. So the opposite over the hypotenuse is equal to the sine of C. So I don't know if this is going to jump or not. Nope. So the sine of C is equal to opposite over hypotenuse. There it is. Multiply both sides by B, and we've accomplished our goal. We've rewritten H in terms of little b and capital C. So we're going to substitute this H right here. We're going to substitute in right there. And we get our world famous, works for all triangles that were given two sides, and the included angle. So yeah, don't be freaked out that, oh, but they didn't give me A and B, they gave me B and C. It doesn't matter. The two letters here represent any two sides, and this represents the angle between them. So generalize, generalize. Hey, the same thing works for an obtuse triangle. I am going to skip that derivation because it's the exact same. So that's it. You're like, I know. You're like, come on, no. I really want to keep, oh, you know what? I have a picture. I just want to make sure that you see this. There it is. It's really important that you recognize that this formula works when you have two sides and the included angle. Top angle, what it just doesn't matter. It just doesn't matter. Think of AB as any two sides and capital C as any angle, or not any, the angle between those two sides. All right, you're walking along the woods and what? There's a triangle, 9 and 10 and 40 degrees. And you're like, God, I can't keep going without finding the area. And we notice that we have the side angle side. That's good. So 1/2 A, B sine. Capital C, it's really, yeah. And there it is. We start with the general, we go to the specific, we plug, and we chug. Nothing too difficult. We can move on with our lives now. What do I struggle with is your ability to honor what's given and what formulas work. This is the area. We're going to do a few more formulas, so it's important to be organized. Hey, look at that. Does it work for the obtuse triangles? Absolutely. Remember the sine value, let's see, the sine value as you go from 0 to 180, which is going to be all possible angles inside a triangle, are all positive. The sine are the y values. So that's kind of cool to recognize off the unit circle. Hey, plug and chug. 1/2, first side, the second side, and the sine of the angle. Hey, I'd say make sure you're in degree mode. Sometimes that messes with people. You're good to go. So how do we mix this up? We find triangles inside bigger objects. So in a regular hexagon, this is something that you just want in your back pocket. If you run into a regular hexagon, you got to know that the 6 pieces, if you're going to cut this up into all the pieces, they are all going to be equilateral triangles. And if you don't have that in your back pocket, this is kind of a tough problem. So the side lengths are 12, so we know this. That all the angles of equilateral triangle are going to be 60. So right there, you have like way too much information. What do we need to do? We need to find the area of this triangle and multiply it by 6. And you're like, I got 3 sides, I know all the angles. Well, what do you need to find to use that formula? You need 2 sides and the included angle. 2 sides and the included angle. Doesn't matter which 2 sides you pick. No, let's pick this one and this one, and we'll say we know that angle. Plug it in, hit enter, multiply by 6. Why multiply by 6? Because there's 6 pieces in that hexagon. Hey, if you want to simplify a general equation, come up with a formula for a hexagon with side length L, now we're talking. Now you have my attention. That's good stuff. All right, 12 is a problem on your homework that nobody quite understands, and there's always one person, got it, they scream, and they're all excited. So we're just going to give you a little hint. We have these 8 coins. They fit exactly on this. What they're looking for is a fraction of the 5 note that is not covered. So you're basically finding how much of this over the total. So you got to know that when you look at a 12-sided dodecagon, and luckily I have the equipment to make a nice drawing here. This, oh, you little turkey. This little, this is the center. If we were to be able to find the area of one triangle, we can multiply it by 12 to get the area of the whole thing, and then we could find the area of everything. Here's the key. We don't know this, but if you just make it x, then you can find the area of this in terms of x, which means you can find the area of all 8 in terms of x, but can you find the area of the rectangle in terms of x? And that's going to be your challenge. I think you got it. I think you can do it. Come on. All right, last one. This is using our newfound formula, the area of a triangle, but it's kind of relying that you know the area of a sector remember, a sector is a piece of pizza. So if you're to find the area of that sector and then subtract the area of this triangle, oh, that is awful picture. Holy mackerel. Let's do that again. Man alive, how in the world are you supposed to understand that? Here is the sector, the piece of pizza, and here is the triangle. Very important, straight line. Okay, you know this and this are the radius, so you know if you know the radius, you know 2 sides. Hopefully you can figure out the angle between those 2 sides. And you see that when you subtract those 2 areas, you get that, which is called the segment. If you go to Walrus and you have an ice cream cone and it's that area, that mound of ice cream, sort of 2-dimension, kind of works, kind of doesn't. All right, check it out. So how do you find the area of a sector? Well, it is a fraction of the whole. Look at that. Look at that. That is a really cool formula. Pi r squared is the area of the whole circle, right? And theta over 360, I use 360 because we're working in degrees here. 135 over 360 is kind of like a fraction of the entire area. All right, so we're going to get, when we do that, we get 57.7. That's the area of the sector. That's the whole piece of pizza. Okay, now let's move me out of the picture. The area of the triangle, 1/2 AB. So I know two sides of the triangle, and do I know the angle between them? You bet. I know the sides are 7, and the angle between them is 135. So I multiply this out. This is the area of that triangle, and when I subtract the 2, I get 40.4. Hey, put this to work. You're going to do great. There you go, 15 minutes-ish. Have an amazing day.